right, welcome. Oh, I forgot which camera I'm using. Welcome everyone to Space Club again. Everyone's welcome to Space Club, and you're here. And today we're talking about the inner planets, which aligns conveniently with my course that that some of you who are watching this are in. So as usual, we have Dr. Phil Stooke and Dr. Tanya Harrison, along with myself. And we're going to be talking about missions to Mercury and Venus and the history of Mercutian, Phil?
Well,
No?
I don't know. Mercurian? I'm not sure.
Mercurian. Kind of like mercurial.
And Venetian? Or Venusian?
Venusian, I think. Yeah, Venusian.
Venusian. Oh, okay.
So.
The history of those explorations. So, but, okay, first, Phil, I know you have a lot of slides and we will get to them, but there's a lot of space history yesterday and today. So we have to touch quickly on some of them. So the first one, November 9th, 1967, the flight of the first named Apollo mission, Apollo 4.
Mm.
So first flight of the Saturn V in its full glorious form. First test of the third stage's launch or firing once in orbit. So that hadn't been done up until now. So Phil, as I'm sure you know, there is no such thing as Apollo 2 and 3. And Apollo 1 is a honorary name to the tragedy of the test flight for what was to be the first crewed mission. But yeah, essentially before Apollo 4, there was the 3 test flights, and then the retroactive dedication for Apollo 1. So Apollo 4 uncrewed, but first test of the Saturn V. First test.
Just carried a sort of boilerplate version of the command module, I think.
Yeah, I was going to say, but I kind of stopped myself halfway because I couldn't remember if that was the first flight of the CSM or not. But yeah, so first flight of the biggest rocket ever, for those of you keeping track. And to this day, yet to be surpassed by a rocket that has been to outer space. So in theory, larger rockets do exist, but they have not made it to space. Okay, we will talk about this, so I can brush over it really quickly. Venus Express launch date today in 2005. So 18th year anniversary of that. And then Tanya, I saw you tweet somebody's birthday would have been their 89th.
Right. It's Carl Sagan's birthday.
Yes.
Sure, he inspired many people that are watching to stare up at the cosmos with wonder.
Yeah.
So, huge impact on my life, huge impact on most stargazers' lives in general, I think.
Yeah. So died quite young in 1996. Would have been 89 today. And wrote, as I went through his kind of Wikipedia rabbit hole, fell upon a book he wrote called The Demon Haunted World. Which sounds like something. Phil, have you read it? Or
no, I haven't read that one actually, but I know about it.
Yeah, it sounds like actually something like it's essentially about the scientific method and trying to explain it as simply as possible, which actually sounds incredibly relevant as always, but probably something I'll dig into. So yeah, Carl Sagan would have been 89 today. So that's today. Tomorrow, I just wanted to quickly look ahead because it was a gold mine. 1970, so 53rd anniversary of Luna 17. So the first ever rover anywhere, which was aboard Luna 17, Lunokhod 1, 53 years ago today. On this date in 2008, a Mars mission was deemed dead.
Phoenix.
Yeah. Yeah. So 157 sols, 5 months of operations. So pretty good. And then would have been, and I didn't realize he died so young, 90th birthday of Ron Evans.
Wow.
Yeah, but he died in 1990, so he died quite young. but the last LEM pilot, no, not LEM pilot, CSM pilot,
Yes.
to orbit the moon, and one of the last unlucky 3 to travel to the moon but not go down. But Apollo 17, of course, with Jack Schmitt and
Gene Cernan.
Right, last person on the moon. So yeah,
who said once he didn't want to die, still having been the last man to walk on the moon, and he was when he passed away, which is still quite sad.
Yeah, that's right. Yeah.
There's a story that I'm actually really, really curious about from an astronaut health perspective. But just jumping into Ron Evans' wiki page again, his biographer indicates that just before he put on his suit, he finished a cigarette and then went cold turkey, or allegedly cold turkey, during the mission, which to me doesn't seem like something that would be allowed to be done. But I don't know if it's just an apocryphal story that's grown in legend since, but it just seems like that's not the environment to undertake caffeine or nicotine cessation.
Yeah, I would be surprised if you could actually smoke in the room where they were getting ready to get into the suit.
Too.
I mean, it would be,
and in the suit. So
yeah, but it was a different era where everybody smoked like chimneys.
That's
so
true.
You never know.
It was, yeah.
So that's yesterday and today, but that's not what we're here for today. We're here to learn about Mercury and Venus. So, Phil, I believe you have some images for us.
Okay.
All
right.
Is that Mercury and Venus together?
Well, that's Venus on the chariots and Mercury behind, and their child Eros flying in front of them.
Oh, they're an item?
They were.
Oh, interesting. Are other planets items? Well, I guess Jupiter was with everyone.
Oh, yeah, that's right. Yeah, he wasn't too fussy.
Yeah. Interesting. I had never even thought of that.
I feel like that needs to be a whole nother lecture, is like the mythology behind all the planets.
Yeah, that's right.
I'm in. Yeah, okay. What was their kid's name?
Eros.
Oh, well, he has an asteroid.
That's right.
Oh, okay. He's the god of love, or eroticism, I'm going to assume from his name.
Let's call it love.
Okay.
This is family friendly programming, Danny.
That's right. Okay. So this is just a couple of pictures showing these two planets roughly to the right scale, and they're very, very different from each other, and you can see that they look pretty different here. So let's just move on and have a look at Mercury first. And Mercury is very, very difficult to actually observe from Earth telescopically. I've got a picture there that just shows the very fuzziest of markings. The problem really is it's so close to the sun that you can't look at it at night, really, when the sun is below the horizon, because Mercury is below the horizon too. So you might just possibly catch it just after sunset when it's at its greatest elongation. But then you're looking through a thick atmosphere, and people have generally found the best way to view it is during daytime. You want to catch it when it's as far away from the sun as possible, but you can see it during the day if you know where to look. But then it's against a bright sky. It's just difficult to study it. And the only exception to that really is that with Earth-based radar, big radio telescopes, we can bounce radar off the planet and reconstruct the echoes that we get back to make images. And so quite a bit can be seen with that, including this particular view here, which it shows the North Pole of Mercury, and very clearly identifies craters there, which you wouldn't even have a hope of seeing in a telescopic image from Earth. And the bright patches inside those craters appear to be reflections from water ice that has been trapped in those permanently shaded craters. And that was discovered well before anybody had discovered clear evidence that we had that on the moon. So very close to the sun, but still water ice in these shaded craters. Okay, let's go on. So we did discover, of course, that there were plenty of craters when we could first fly a spacecraft past it. The first spacecraft was called Mariner 10. And the Mariner spacecraft were a series of spacecraft that was sent off to Venus and to Mars, kind of alternating one and the other. Mariner 10 flew past Venus and onto Mercury. That was the first time that we'd used a gravity assist to get from one planet to another. And that's something that is done a lot today and enables things that you just couldn't do otherwise. Well, this was the first opportunity to do that. So Mariner 10 flew past Venus and just photographed the clouds, which we'll be seeing later on. And then it arrived at Mercury. It didn't go into orbit. It just flew right past the planet. But on its approach and then on its departure, it took lots of pictures so that we got the chance to actually view about half of the planet, the half that was actually illuminated at that moment. And superficially, it looks a lot like the moon. So let's have a look at the next slide there. And when we get in a bit closer, you can see the craters. You can see kind of smooth but slightly wrinkly plains between them, very much like our moon, except that on the moon, the smooth plains are dark, chemically distinct from the rest of the surface. And on Mercury, there isn't any obvious connection like that between the light and dark markings and the smooth plains. So that's a difference. There's one really gigantic impact basin. A basin is just a really, really big crater. And we can see about half of it there, a sort of semicircular arc on the left-hand side of the image. And that's a really big crater, a basin, which is called Caloris, which just means hot. Otherwise, the craters that we see get named after artists of various kinds. The craters on the moon were named after scientists, and when people started mapping craters on Mars, they named them after scientists too. Well, Mercury was the third world to be mapped like that, and people thought, well, you know, we should recognize other types of worthy folk to name craters after. So they chose artists, and I use that term very generally: painters, sculptors, musicians, writers. So people like Shakespeare and Beethoven are there. Lots of different kinds of artists. So Mercury superficially is like the moon, but there is a really big difference. Mercury is much denser than the moon, and it has quite a significant magnetic field, which the moon doesn't have as a global entity. It just has a few little magnetic anomalies here and there. So the suggestion is that Mercury has a large core of iron, which makes it quite different from the moon. Okay, let's move on there.
I'm just Googling who has a bigger crater, Beethoven or Mozart, and Beethoven has a way bigger crater. But now I'm curious if he has the biggest composer crater, because, does Bach have a Anyways, carry on. I'll come back with updates.
All right. Okay, so now this fellow is an Italian mathematician called Giuseppe Colombo, who realized long before NASA did that if you fly past Mercury and out the other side, as Mariner 10 did, that you're just going to end up in orbit around the sun. And if the period of that orbit is adjusted just right, you would come back to where Mercury was after 2 Mercury orbits. You'd come back to the same place. And so he pointed this out to NASA, and they hadn't realized it. But they ended up getting 3 flybys of Mercury because of this. So that was very good to know, and we'll be meeting Giuseppe Colombo later. So the next Mercury mission was Messenger, a NASA mission that launched in 2004, and it orbited Mercury from 2011 to 15. So it took from 2004 to 2011 to get into orbit around Mercury. That's a long time. And you might wonder just why it would take so long, because it's not that far away. But the reason is that if you come flying into Mercury like Mariner 10 did at very, very high speed, then you need a big rocket to slow yourself down to go into orbit. It would have just been too big for a rocket for Mariner 10. It would have been all rocket and no spacecraft, basically, if it was going to go into orbit. So instead, when we fly from Earth to Mercury, we don't want to just go direct and end up going really, really fast. So the spacecraft loops around. Messenger flew past Venus. It flew past Mercury and then back again and flew past Mercury several times. And each time it flies past a planet, it's using the gravity of that planet to adjust its orbit a little bit until basically the goal you're waiting for is that the spacecraft's orbit around the sun is very similar to Mercury's orbit around the sun. So the relative speed between them is not great. And then you just need a small rocket to get into orbit. So they take a long time adjusting the orbit with planetary flybys so that it's easy to go into orbit later on. We have another spacecraft doing exactly the same thing right now called Bepi Colombo, which we'll come to later. Okay, so this spacecraft was very capable. The thing is about Mariner 10 was that it only saw about half the planet with 1970s instruments. Messenger was able to study the whole planet using modern instruments. So we had maps of the composition of the surface, global topography, basically the magnetic field could be mapped and so on, stuff that Mariner 10 couldn't do. So we had a very, very effective mapping mission from Messenger and really got to know Mercury quite well from that. And of course, we also got these very high resolution images. So instead of looking just at pictures of craters on Mercury and that sort of thing, let's look at something special. This is a very unusual feature here. There are lots of them on Mercury, and they're called hollows. Nobody knows exactly what's going on here, but the general impression is that volatiles, that is, anything that might be evaporated by heating, might be in the surface materials, and when it evaporates, it blows away the surface materials to leave these hollows. Now, that might be sulfur or sulfur compounds like sulfur dioxide. It might be gases like water vapor or carbon dioxide, possibly. There might be other things we could think of as well. We don't know what that volatile is, but something that evaporates when it's heated seems to be blowing out of the surface and leaving these hollows. And there are lots and lots of them. And there are just a few of these on the moon as well, quite small, called irregular mare patches, which might possibly be produced the same way, although people are spending a lot of time trying to find a volcanic explanation for them. But there are flaws with all of the volcanic explanations too. So it's possible that we have a few of these on the moon, but there are lots of them on Mercury, where it was much hotter.
Sorry.
I was
only half paying attention because I was still looking up who has the biggest craters.
You've got to forget about who has the biggest crater, Danny.
Beethoven has the second biggest crater on the planet. The first is Rembrandt. So I'm okay with that. I'm curious how other composers rank, like Wagner has one, but that's a different discussion. These, so you said people are thinking about volcanic origins, hypothetically.
Well, for the ones on the moon,
right? Okay.
A lot of people would prefer a volcanic explanation, but trying to make it work is very, very difficult, particularly since they look as if they're very young features. One person that I particularly am interested in from this point of view is Peter Schultz of Brown University, who has argued that these features on the moon are also produced by the loss of volatiles through the regolith. And since people seem to agree that that is what's happening on Mercury, I don't see why that wouldn't be happening on the moon. But, well, we'll have to see.
Okay.
So is there no volcanism on Mercury?
Oh, there's lots of volcanism on Mercury.
Okay,
yes,
I thought so.
Yeah.
Just not involved in these things.
No, probably not. There's volcanism producing lava flows, and there are big volcanic sort of calderas and things like that. But these things don't appear to be directly volcanic.
Okay.
But yeah, we still don't really know very much about them.
Okay.
Okay,
Yeah,
let's go
my
to.
first thought would be, would there be any relationship to the same process that would make skylights, if that's what they're still being called?
Right, drainage into subsurface voids. I suppose you might be able to make that work in some cases, but some of the hollows are much bigger than this, and I can't quite imagine how that would work.
Okay.
These are just a few kilometers across, these features. Okay, so here's another thing that's unique to Mercury. So basically, first, of course, we've got lots of craters in this image, including one rather large one. And that large crater is filled in with smooth but slightly wrinkly plains, and those would be volcanic plains. Those would be lava flows, almost certainly. And they're widespread on Mercury. Mercury has more lava flows than the moon does. So it's been more volcanic. But the significant thing here is this great big dark shadow running across the center of the crater. It's a cliff. The land on the left is higher than the land on the right, so it's a cliff. It's in shadow, but that long scarp or cliff is probably a place where the surface is fractured, and we think that they're produced by compression on the surface. So the left-hand side has been pushed up against and then up and over the right-hand side just a little bit, and has produced this this dramatic cliff on the landscape. And we do see some of these on the moon, but they're generally quite small. So again, I think, just like the moon's hollows are few and far between and quite small, Mercury has lots more of them, and some of them much bigger. These cliffs are much bigger than anything like this on the moon. It's like Mercury it's like the moon, but it's just had more going on, more lava flows, more of these thrust faults that make these cliffs, more hollows. It's been more active. But at the same time, there are lots of ancient craters too.
Just want to clarify for the students as well. So planetary geologists will say things like lava and lava flows, and they mean the remnants of these things, unless they're talking about Earth. But I often compare a lot of planetary science to like crime scene investigation. So like you could say there was a lot of blood at the scene, but it's probably blood stains, right? It's the remnants of these things.
All right.
So I don't want to confuse the students that there's any active.
Yeah, no, that's it. Okay, that's a very good point. So we should definitely say that. So on the moon, it looks like you don't have any very young, active volcanoes. And that's one of the reasons why those hollows, you struggle to find a volcanic explanation for them, because they look sharp-edged and young, but volcanoes ought to be much older. Here on Mercury, I think the lava flows probably went on for longer, but even so, we don't expect to see active volcanoes pouring out lava flows now. So yeah, these are old features.
Third hypothesis about these holes. Again, not a planetary geologist. Things in space tend to get hit by other things.
Right.
I guess you'd have to have quite cavernous, like the moon would have to be more cavernous than we think, or have a bunch of hollow portions for like meteorite strikes to hit and then cause these. Does it make any sense?
Well, I think we know how impacting objects behave now. I think we can say that if an asteroid smashes into the moon or Mercury or Mars, it's going to dig a crater. It's not going to just cause sort of local collapse into little pits and things like that. It's going to make
so fast it punches right through, clean hole. I don't know, maybe I'm
That's not how impacts work, though.
well, sometimes you just gotta think different.
Well, I guess so.
Just to
However, I'm
remind
sticking
students
to
that
my
Danny
guns.
is not a geologist.
If these are, I can't wait for 10 years from now when someone submits an abstract LPSC. Maybe
They
it'll be me.
cite Space Club as
Yeah.
the source.
Yeah.
All right. So here we have a different thing. We're looking at craters again. On the left-hand side, we're seeing craters sort of obliquely from a distance, and I think the coloring it represents the temperature of the surface in that view. And if you get up to near the poles, parts of the craters never see the sun. The sun can't shine into those polar craters, and therefore they're very cold. And when Messenger took pictures of those shaded areas, but long exposure pictures, so it could actually see the surface just lit up by a little bit of light reflected off nearby hilltops and that kind of thing, it could detect what looked like patches of sort of smooth, bright patches in some areas, smooth, dark patches in other areas, but corresponding to these very shaded areas, permanent shadow areas. And we know from the radar reflections that they reflect radar very strongly, which is a characteristic of ice. So it's thought that these are ice deposits in the polar craters. Some of them are perhaps relatively clean ice, and some are very dark and may be colored by organic materials, carbon compounds, things like that. At any rate, there's something very interesting going on in those polar craters. And the same thing might be happening on the moon.
Fuller crater is named after Richard Buckminster Fuller, an American engineer and architect. I only looked that up because I see that Prokofiev's crater is larger than his.
Okay. All right. So what's coming up next? Messenger really told us a lot about Mercury, but there's another spacecraft on its way, and that's a European spacecraft. Actually, I should say this is a joint European and Japanese mission. ESA, European Space Agency, and JAXA, the Japanese Space Exploration Agency. They're sending this mission jointly. There are two orbiters. The little one is the Japanese one, and it's going to study the magnetic field. And the larger one is the European orbiter, and it will study Mercury with cameras and all sorts of other instruments like that. And I should just say that this mission is called Bepi Colombo, and that was the nickname of Giuseppe Colombo. So it's basically named after him in recognition of his important observation about the Mariner 10 mission. Okay, so that's coming up. This spacecraft will go into orbit in 2025 after 7 years of flight. So it'll take a while, as I said.
It's kind of crazy that it takes just as long to get to Mercury as it does to get to Saturn.
Yeah, that's right. Yeah.
No landers.
No, there was a plan to have a lander on this mission, but it had to be descoped. They had to cut it out. They couldn't make the mission big enough to carry a lander and still do what they wanted in orbit. So that will have to wait for the future. But people are thinking about Mercury landers for future missions.
Yeah, I imagine. I mean, regolith as usual, but because of that presumed giant core, I think a seismometer would be really, really interesting just to try to narrow down how big is that core and what's the deal with Mercury.
Yeah, and I'm sure that they would think of doing something like that. It's going to be a little bit tricky to operate on the surface of Mercury all the same, except perhaps near the poles, just because the surface temperature is so desperately high. That would definitely take some doing. And I know that some people have talked about landing near the evening terminator and operating for a few days before sunset, and then surviving through the night with a little radioactive heat source, and then waking up at dawn to continue something else. So that, and conceivably a seismometer could work through that that night time and record all its data and then transmit it back later.
Tanya, Martian, thoughts on Mercury?
Mercury is really interesting. I'm fascinated that we can see the North Pole of Mercury with Arecibo here on Earth. Like for some reason that just blows my mind. And it sucks that it takes so long to get there. Like I remember Bepi Colombo launching, and then you just kind of forget about it because it takes so long to get there. So it'll be really cool to see what we learn from this mission, because it seems like there's so much we still don't understand about Mercury.
Yeah, that's right.
All right.
Okay.
Let's go to Venus. Earth in 10 years.
Yeah. All right. Venus. Here we are. So, yeah, this is another planet that's difficult to study from Earth. It can actually come closer to us than any other planet. But we didn't know much about it until spacecraft started arriving. It's completely covered with clouds. So people spent a long time looking at Mercury and thinking they were seeing fuzzy surface features, but they were really just seeing markings in the clouds. People didn't even know how the planet rotated until relatively recently, when they were able to reflect radar echoes off it. And that was how they discovered how Mercury rotates as well. Just bouncing radar off a planet, you get some information about rotation. And it rotates in a very strange way. It rotates backwards compared with all the other planets, as if its North Pole is pointing south. And it rotates extremely slowly. It takes longer to make one rotation of the planet than it does take for the planet to orbit around the sun. So
yeah, like early telescopic observations, like staring at it for 6 months, it would move, but like, was anyone hypothesizing, like, does this thing just not spin at all?
Well, it isn't easy to have something that doesn't spin in space, because any little disturbance would start it.
Yeah.
But yeah, well, I don't know. The thing is, it rotates so slowly that it almost might as well not be rotating. It goes so slowly. But I think actually, what people thought before the radar discoveries of the real rotation periods of Mercury and Venus was that they rotated like our moon does, in a synchronous rotation with the thing they're orbiting. So people thought that Mercury always kept the same face towards the sun, and Venus might as well. So that was one possibility. Then just before we got the radar data, some French astronomers noticed that the cloud patterns seem to repeat every 4 days, 4 Earth days. So they thought that might be the rotation period of the planet. But actually, the whole atmosphere blows around the planet much faster than the planet rotates. And the clouds do rotate in 4 days. That's true, but at least the upper layer of clouds.
Yeah.
But the planet itself doesn't rotate like that.
Okay, cool.
All right, so atmosphere, yeah, it's very, very hot and very, very dense. If you were on the surface of Venus, you'd be experiencing 90 times our sea level pressure, which is, pretty drastic. You couldn't really cope with that. And the temperature is even worse, 450 Celsius, very, very hot, hot enough to melt metals like lead, for instance. So it's a very difficult place to study. If you put a lander on the surface, it's not going to survive under those temperatures for very long. No lander has survived more than 2 hours. So it's a difficult thing to do. But the atmosphere is interesting. It's mostly carbon dioxide. It's got clouds containing sulfur compounds, including sulfuric acid. So a really rather unpleasant place. We've got a couple of pictures here showing a vortex at the North Pole, where the atmosphere is rotating and it seems to be sort of gurgling down this whirlpool at the pole. And as you go down, it gets hotter and hotter. So the infrared image on the left shows that increased heat as you go into it. It's a very difficult place to operate on the surface.
Yeah, I remember, and old space club at Western. Something it observed, it might have been Akatsuki or just a paper, but like severe wind shears where you have layers of the atmosphere almost like going counter to the dominant layers. So you get to like this incredible wind shear that people were observing. And I think Akatsuki was trying to see more of that, if I remember.
Yeah. Yes, and they noticed that you get this enormous, almost planet-wide shock wave in the atmosphere. Well, it's not really a shock wave. I shouldn't describe it as such, but a big wave in the atmosphere when the atmosphere is flowing across one of the highland areas on the planet. Yeah. So, yeah, and actually, the atmosphere is very hot at the surface, but it's quite cold at the top, up in space. On the edge of space, the top of the clouds are quite cold. So the temperature is increasing as you go down. So if you study Venus with infrared instruments and you map out the temperature distribution in the clouds, you can actually kind of map out what's happening in the clouds at different depths in the different temperature regimes as you go down. All right. The first few spacecraft that went there, and I'm not going to list them all, quite a lot, they flew by and they took pictures. One of those was Mariner 10 on its way to Mercury, taking pictures of the clouds. Or they would fly by taking temperature measurements and things like that. So the first mission that really did something quite dramatic at Venus here was Pioneer Venus, which went into orbit and also dropped 4 probes into the atmosphere. So we could get things like the temperature, the composition, the wind velocity, and so on, all the way down through the atmosphere in 4 different places. And that was a very significant mission. And the orbiter mapped the planet, mapped its topography, took some very low resolution radar images. So that was quite a significant event in the exploration of Venus. What about going to the surface? Now, those early years of Venus exploration were shared by the Soviet Union and the United States. And then the Soviets sent quite a few spacecraft. And one of the things they really focused on was trying to get down to the surface. So they dropped quite a few landers. 4 of them actually succeeded in landing safely and operating on the surface and taking pictures. There were others that landed but couldn't take pictures for one reason or another. But 4 of them did. So here we actually have surface views of Venus. Venera 9 and a companion Venera 10 in 1975 took pictures. There's like the black and white one at the top, that's just showing boulders scattered across the surface. And Venera 10 shows sort of flat rock slabs and gravelly soil. And then in 1982, another pair of missions, Venera 13 and 14, landed, and Venera 14 here photographed these sort of flat slabs of rock. So we've seen different kinds of landscapes, but these missions only operate for really quite a short time. You'll notice on the left-hand side of the color image, there's a kind of arm reaching out from the spacecraft. That was designed, it was sort of mounted vertically, and when the spacecraft landed, that was supposed to go plop down onto the surface. And a little probe on it would dig into the surface to measure its hardness. It's called a penetrometer. It's designed to measure how hard the surface is when you hit it. But it landed on, you can vaguely see that it's landed on something there. That is actually the cap that protected the camera during descent through the atmosphere. As soon as the spacecraft landed, it popped off its lens cap onto the surface, and then the arm went plop right on top of the lens cap. So very unfortunate, but that's okay because they got those measurements in other places as well.
You could infer them. You could just remove the lens cap from the equation and just figure out what was the rock underneath.
I look forward to reading your paper about it then.
Inferred rock hardness.
All right, so let's move on here.
Actually, I have a question about the Venera 14 image.
Oh, yeah.
So there's a color scale on the
Yes.
right side, but it looks really dusty or dirty, or is that just the color balance of the image?
There might be a little bit of dust on it, but a lot of that is caused by the illumination, because it is being illuminated by a kind of orangey sky.
Oh, right.
Sunlight filtered through the atmosphere, plus whatever dust and haze is in the atmosphere, makes the sky orange on Venus. And we do know that because these panoramas actually extend out to the horizon, and you can just see a bit of the sky, although I've cropped them off there. But it's illuminated by orange light. But you can take that same image and process it as if the orange color is taken out, and then your color scale looks more realistic. That's what you would see if there was no atmospheric haze on Venus. But what you actually see when you're there with the haze is what you see in this image.
So Venus is in sepia.
Yeah, that's right.
Oh.
Okay, so how are we going to study the surface? We can study the atmosphere with orbiters. We can drop landers on the surface. But if we want to map the whole planet, we need something else. And the answer is radar. We can use radar from the Earth. And that's what these images are. But they're difficult to interpret. The thing about radar is that it reflects very well off rough surfaces, but rather poorly, at least coming back to us, off smooth surfaces. Now, it doesn't really reflect poorly off smooth surfaces. It's just that if the surface is smooth, the reflection goes away from the Earth. And if we're trying to send a beam from the Earth to Venus and get a reflection back, it's going to work best if the surface is rough, because that scatters the radar in all directions, including back to Earth. So when we look at those images, we know that the bright areas are rough. They're covered with boulders or other kinds of rough surfaces. When we see dark patches, like the one in the middle at the top image there, that's probably quite smooth. We don't know whether that means it's covered with dust or whether it's covered with very smooth, let's say, lava flows or something like that. But so they're difficult to interpret, but you know where it's rough or smooth. But we can't tell if the rough area is high or low, not just by looking at those images. So we have to do something better than that. And the best way is to use radar from an orbiter, which you can point in a certain direction, and then you know what direction the radar is shining in, and what is coming back to the radar can be more easily interpreted. So let's look at the next image.
I'm wagering low. I think.
Well, most of them are high, but anyway, never mind. Okay, so anyway, so here we have radar images from an orbiting spacecraft, Magellan, an American orbiter. And let's think about the bottom image first. It's got these circular markings.
Pancake.
No,
Aren't they called pancake domes?
They are pancake domes, yes.
Uh-huh.
So they're domes, raised features, but with quite steep, sharp edges around the outside. But you could look at that and say, well, that looks like a crater to me. But the question is, which way is the radar pointing? So the radar is on the spacecraft. It's not looking straight down. It looks off to the side. And if it's looking off to the side and it encounters a steep slope facing towards it, it'll reflect very strongly back to the spacecraft. And if the slope's facing away from it, then you'll hardly get any reflection at all. So because we know what direction the radar is shining in that, we know that actually those things are raised. The bright curve on the left-hand side of the domes is a steep slope rising above the surface to the top of the dome. And the spacecraft is illuminating it with radar from the left. So those are volcanoes, and there are lots of them. The one at the top, which sort of superficially looks similar, a dark, roughly circular marking with a bright edge, that's a crater. The light's shining, the radar, is shining in the other direction. And this is a big impact crater. And its ejecta included quite a lot of melted material, which has flowed off to the lower right like a great big lava flow, a big impact melt flow. You get much more of that on Venus than you do on the moon. We do see impact flows like that on the moon, but much more on Venus because the surface is already much hotter to start with. So it's easier to melt stuff. And it would stay hot for longer. Okay, so there are a few craters. Mercury has lots of craters. The moon has lots of craters. Venus just has a few. You have to start looking for a reason for that, of course. And the best explanation is that the craters were there, but they've been covered up or destroyed in some way by geological processes. How can we be sure they were there, though? I think you could kind of ask that question. The thing is, there's no sort of vaccination that you can give a planet to stop it being struck by asteroids. It's going to get impacted. And if the moon is covered with craters and Mercury is covered with craters, Venus and the Earth, Mars, they ought to be covered with craters too. And if you find a planet where it's not covered with craters, something's happened. There must have been craters because you can't prevent them from happening. So something has happened to them and they've been covered up by lava flows or destroyed by erosion or whatever it might be on different planets. But on Venus, they've presumably been covered up by lava flows. Okay, so let's look on. Our next picture shows one of these lava flows. This is an absolutely gigantic field of lava flows, more than 1,000 kilometers across in this image, and it's a much, much larger field of lava flows than that. Coming in from the left and way off hundreds of kilometers away to the left is a big volcanic complex. The lava has flooded out in a vast flood across the surface, and until it butted up against a linear ridge, which runs from north to south in this view. And the lava built up in a pool until it overflowed in the center of that ridge and out the other side and made another great big lava flow on the right-hand side. So there are big areas covered with lava. We've got this sort of funny mottling of light and dark, and the darker stuff is rougher. The darker stuff is smoother and the brighter stuff is rougher on that, just in these different parts of the lava flows. So a very active planet. And this is one place where you might, in fact, have active volcanoes. Venus is about as big as the Earth. And just as the Earth has active volcanoes, Venus probably does too. And we're beginning to get the first evidence that we might be seeing active features on the surface now. Here's some little volcanic cones. There are literally millions of these across the surface of Venus. Tiny little volcanic cones. They might be, in this case, they're probably only 3, 4, 5 kilometers across. Maybe the bigger one is about 10 kilometers, something like that. Surrounded by lava flows. There's a rough, bright lava flow on the right, and a darker, older lava flow on the left. So this is almost exclusively a volcanic landscape. And even more lava, in this case, huge lava flows covering immense areas. But as they cool and crust over, the lava can continue to flow underneath them and create lava channels. Some of the channels might actually be channels of active lava flows at the surface, and some with subsurface flow where you get a lava tube and then the roof collapses and you get a channel like this. And can't look at it and say specifically which way this worked. On Earth, we have lava flows that have been buried as lava tubes, and then you get a collapse of the roof and you see the channel. But we also have lava channels where the lava just flows at the surface. I don't necessarily know which way around this worked, but these long channels, they're quite common on Venus, and the longest one is 6,000 kilometers long. So these can be quite big features. And there are also long mountain ridges. This is just part of one of these, part of Acna Montes. It's just a big mountain ridge. We don't really understand all the details of how these features have formed, One thing that Venus doesn't seem to have is the kind of plate tectonic behavior that we see on Earth, where the continents are kind of rafted around by giant convection currents deep in the Earth, and they move around, and if they collide, or like two continents can collide, like Asia and India, and push up the Himalaya mountain range between them, it's not so obvious that that's happened on Venus. In fact, it appears that we don't have that, but there must be something happening perhaps on a more local scale, where things can push against each other and push up a mountain ridge. So we do see some of those, and some of them are quite big and dramatic.
No, I won't even, never mind.
And there are also plenty of these very rough upland surfaces that are intensely cut by fractures. They're called tesserae, and they're basically just hilly areas that have been cut through by fractures. So the surface is very rough where it's been fractured, often with fractures cutting in multiple directions to really divide up the surface into little chunks. And there's some suspicion that they might be remnants of an earlier crust on Venus, an earlier part of the planet's history. We have to come back to the fact that there aren't very many craters. And if there aren't very many craters because most of the surface has been flooded over with lava, then some of these sort of upland areas like this, which stick up above the lava flows and are intensely broken up by fractures, might be remnants of part of this older crust that might have some craters in it. And every now and then you see little roughly circular markings within them that might be ancient craters. But we don't really know a lot about the geology that is created, the processes that have created this kind of landscape.
If you showed me that quickly, I might think it's just one of the ice moons. Like it looks kind of like the ice with the brine coming through of Europa.
Yeah, it would be easy enough to mistake it for something like that. It's true. Yeah. So quite an active place. So this is, now here I've come back to Mercury. This is a Bepi-Colombo image of Mercury taken during one of the flybys. And it clearly shows the way that much of Mercury is just totally covered with craters, wall-to-wall craters of all sizes, just like on our moon. And that's what we don't see on Venus. So there are no places where we see this kind of very ancient surface. But if this surface was being buckled and twisted around by flexing in the crust, so that it was all chopped up by fractures, that might create the tesserae, and then large parts of that kind of broken up surface could be flooded with lava, and that's covering up more of the ancient surface. So basically this old surface hasn't really survived on Venus, and we may indeed actually have active volcanoes there. So the modern surface of Venus is quite young. So what does it look like if we map this on a global scale? It seems that Venus is almost certainly geologically active like the Earth, but it doesn't have plate tectonics that create features exactly like we see on the Earth. This is a map showing most of Venus except for the polar regions, and it does show some upland areas. So yellow is highland. There's a red bit, which is an extremely high area called but most of the surface is lowland. Now, suppose we looked at Earth mapped the same way. Earth has oceans, but Venus is too hot for oceans. So imagine the oceans evaporate away. What you see on the Earth would be these gigantic high plateaus, which would be the continents. And some of them have extra mountain ranges on them, like the Western Cordillera of North America. So you'd see this kind of pattern of highlands and lowlands on Earth if you stripped away the oceans. But generally speaking, Venus has much smaller continental type uplands, and most of the surface would correspond to the ocean floor. And why are these two worlds so different? And this is, I think, a good little lesson in planetary geology here, that at least for the rocky inner planets, the kind of basic rule that we have is that the bigger something is, the hotter it can be inside and the longer it can stay hot. So Earth and Venus are big enough that heat that was generated as they formed, and also through radioactive decay of minerals later on, that heat is trapped inside them, and it has lasted for the whole lifetime of the solar system up to now. And if the heat sources stopped, they'd stay hot inside for a long, long time, for probably billions of years anyway. So they're big and they can stay hot, and that heat drives geological activity, mountain building, volcanoes, continental movements on the Earth, maybe regional movements on Venus, that sort of thing. But they're big. But smaller worlds, they cool down faster. They would have less heat to start with. They cool down faster. They can only stay active with volcanoes and things going on for a relatively brief time. So a couple of billion years or so on the moon, maybe longer on Venus, maybe 3 billion years, something like that. But eventually they run out of that energy, and they cool down, and they're not so active. And Mars, which is intermediate between these two in size, is kind of intermediate in its activity too. It's got some ancient cratered areas that have survived for the lifetime of the solar system, and other areas that are covered with lava flows. It's been more active than the Moon and Mercury, but not as active as Venus and the Earth. So it's a nice little rule just about the size. That doesn't work at all when you get into the outer solar system. That whole idea falls apart out there, where a lot of energy is being produced in moons by tidal influences with the giant planets. But as a basic rule, it works nicely for the rocky inner planets. All right.
Yeah, it's just such a weird planet, Venus. Mercury's, I don't know, it's just, I've always just thought of it as small moon, but like our moon, but smaller and closer to the Earth. Obviously, like you said,
it's a bit more active than that.
Yeah. Interesting. So is it, because I've never even thought of it as really even much of a mystery or controversial, that Venus's, like any sort of impact history on Venus isn't immediately evident. I just assume.
Only the most recent.
Okay.
Yeah. Only the most recent impact. So maybe over the last, say, 500 million years, possibly stretching out to 1 billion years, something like that. Anything that hit in that time is kind of preserved on Venus and visible. But anything older, including right back in the early years of the solar system, when Mercury and the Moon acquired global cratering, that has been completely destroyed on Venus.
I can't remember who proposed the theory, but at some point, wasn't there an idea that because there was so much activity, like building up the crust of Venus, that there might have been one massive resurfacing event where the crust actually just kind of sunk beneath the mantle, and so it was all resurfaced simultaneously?
Yeah, okay. That's right. There is that suggestion. And the alternative to that, which is also out there in the literature, is just that you would have regional events that gradually build up like a patchwork covering the whole planet. And so you end up with the same result, but it's in small regional patches instead of one single global event. And I don't really know how you would distinguish between those two.
One makes for a better movie than the other.
Well, that's true. Yeah.
Or better paper.
Yeah.
I still, like, I'll catch myself when I'm saying, when a student asks about Venus's like geological activity, I'll say, well, it's thought that there's volcanoes, but it hasn't been confirmed, which to me is wild that something that pretty significant is unknown about our neighbor. But like, obviously the atmosphere doesn't help, but like
Well, the atmosphere doesn't help, no. And also spacecraft observations tend to be quite limited in time. Magellan operated for about 2 years, I think, mapping Venus. So you'd actually have to be mapping that specific bit of planet that was changing, probably sort of twice, say 1 year and then 6 months later or a year later again, to actually see the change. And somebody just published recently a suggestion that they might have caught that in the Magellan images, but one tiny little thing, and actually tiny enough that it's debatable whether it's true. But it might possibly be present in the Magellan images. But there are future missions going to Venus, which are going to map the planet in much more detail, and basically we'll be able to compare those images with Magellan images to see if there really have been changes over, that would be like about a 30-year or 40-year even time frame. So that gives you a much better chance of being able to see a change.
Yeah, because I'm just looking it up now. I remember, because it's quite old. It's not necessarily new, but Eden Mons was the one where the heat signature might have been, Venus Express.
Yeah, Venus Express. That's right. So yeah, Venus Express mapped the temperature of the surface and might have found places, at least one or two, that were a bit hotter than you would expect. So that's a possibility that hints at geological activity. And another thing is the composition of the atmosphere, which has been observed to have brief changes that might be produced by volcanic gases being erupted into the atmosphere. But they're always just sort of possibilities, and the definite proof that something has happened and being able to see where it is and what's happened, we're sort of not really very far advanced along that route. We've got suggestions, but they're not very good yet. But the future missions should really answer those questions.
Yeah, because you could just come across the remnant heat from some sort of event, but I guess just against the background heat of Venus too.
Yeah,
issue.
I mean, really, what I want to see is a volcano that didn't have a fresh lava flow on it in Magellan images, and has a great big fresh lava flow on it in a future missions images.
That would be incredible.
That would be great, and I wouldn't be surprised if we didn't see that.
I'm curious if we start to see how dynamic Venus actually is, if we might be able to get more attention pointed toward it. Like, we know so much more about Mars than we do Venus, and Venus is in its own right a really fascinating place, and it blows my mind that the best map that we have of the surface, I mean, Magellan, I think that was that came out when I was like 8 or 9 years old.
Yeah.
And we still don't have anything better.
Yeah, well, that's true. And Magellan produced great radar imagery. They're lovely pictures. But the topographic mapping we have from Magellan is really, really poor compared with what we have for Mars and the Moon and so on. Ah, there you go. Yeah.
Yeah, this was that old one I remember from probably when I started teaching the course. But and I thought, like, when I started, I was like, okay, like they're on the case evidently anytime now. But I guess then there was a gap in Venus coverage until Akatsuki got there, and now Pepe Colombo.
And Akatsuki is mostly doing atmospheric studies. Its orbit is a bit too high to really work very well for surface studies.
Okay, first question. So we're coming off the Apollo week, or at least when these questions are. So there was Apollo, and then I jumped more into there's the Mars week, and then this week we're doing the inner planets.
Yeah.
So coming out of the Apollo week, we have Apollo questions. In the week 6 podcast, which is with you, Phil, it's one we recorded a little while ago.
Yeah.
It was discussed how before Apollo 16 and 17, geologists misinterpreted the moon's geology at the landing sites. How likely is it that we are misinterpreting the surfaces of other objects and planets? Were there any similar misinterpretations made for Mars geology before the Mars rovers landed? So something I think both of you probably have some insight into.
I think you should answer that, Tanya.
I mean, a lot of stuff that we saw from orbit, we confirmed on the ground, which was pretty amazing. You know, like we knew that we were sending Opportunity to a place where we had detected a hematite signature from orbit, and we didn't know where the heck that was coming from. And then we got lucky within the first like 30 sols of the mission, we found the little hematite blueberries that were causing that signature. But there have been some stuff that confused us in Gale Crater, where Curiosity is at. There were these dark, kind of lightly cratered features in the relative scheme of things that we thought from like high-rise images were lava flows, which were a little bit hard to explain given where they were, but it's like, what else could this be? And they got on the ground and just found out that they were, you know, highly indurated mud flows, so really, really strong mud, which is not often the case on the Earth because it's very wet here. And so they've been trying to figure out, well, after they found that, they were trying to figure out, you know, where did those come from instead? And are there other things on Mars that might look like something based on what we guessed it might be, but it's actually, we're being tricked just because we didn't think it could be something else?
Right. Yeah, I would also think about the Spirit rover, which landed in a crater called Gusev. And people had, they went there basically because Gusev looked like it had once been a lake. There's a great big channel, a huge valley kind of that extends into Gusev, Mardim Vallis. Looks like possibly the remnants of a river delta around its mouth, and then it would float out into the crater and eventually filled the crater up as a lake. So you ought to have lake sediments in it. But the rocks that the Spirit rover found were volcanic, and in fact, you know, there were volcanic interpretations of what we were seeing in the orbital images as well. But people didn't really want to believe them because they wanted a lake. I think that might be one thing. And if you had a lake and it dried up, then you might expect evaporite type deposits, say patches of sulfate minerals and things like that. And so there was a little bright patch in among a group of hills. It was given the nickname Home Plate. And people went to that thinking it might be an evaporitic type of structure. And it turned out that it was probably some kind of a small volcanic feature instead. But some of these things were difficult to interpret from orbit and didn't really match exactly what was expected. I think the important thing, though, is that we needed to have those misconceptions corrected. And it's good that the mission actually goes there and does demonstrate that there was a mistake. So, yeah, I would mention that as a possibility for that question too.
Yeah, and I mean, certainly in the case of the Apollo later missions, it wasn't like a catastrophic problem that the geological context was not what we expected. It was, the primary objective was land safely anyways, as it will always be with human space flight. So
yeah,
no matter what, they were going to find something interesting. And they kind of just flipped what they thought 16 and 17 would be inadvertently.
Yeah.
Okay, question number 2. A little bit more in my realm, I suppose, but why do you think the moon ended up as the final destination for the space race? Why stop there and not try to go further? Phil, do you want to, your thoughts?
Well, Apollo was just incredibly expensive. And actually, it's given space exploration a bad rap ever since, because, people now sort of imagine that space flight is just incredibly expensive because Apollo was. But we can actually do a lot of things much more cheaply than we could back in the 60s. Anyway, it was expensive. And the American government was never going to continue funding it at those levels for very long. So NASA had wonderful plans for things that it could do. It would build a moon base. It would go to Mars, giant space stations, all kinds of stuff that they thought they would do. But Congress wasn't interested in putting money into those things, and it scaled everything back. And NASA could have been shut down completely, except nobody really wanted to be the people who shut it down. So they tried to find less expensive things for it to do, and basically that's what happened. But people just didn't want to spend at the rate that that was required for these bigger things, these other destinations.
Yeah, and that's just it. I think the original question, why the moon ended up as the final destination. Also important to think about the retroactive interpretation of the space race that takes place after that happens. So, yeah, at the time, certainly the moon was seen as a primary objective, but there was not inherently the assumption that whoever gets there first wins and then the space race is over.
Right.
That kind of emerged organically as the Apollo program ran its course in terms of public interest and political funding at the same time that the Soviet Union ran into a multitude of problems with getting anywhere near the moon with humans. But if you listen and see some of the news articles from that time, there's a portion of the community, certainly in the US, who are fully expecting Mars to be next, Mars by the 1980s. Spirit Agnew was a big advocate of this. He was a prominent US politician at the time. So in hindsight, it can be explained sometimes a little too neatly that they were racing to the moon, and when the US got there, the space race ended. At the time, it was not so cut and dry. There had been quite a bit of achievement from the first launch in 57 by the Soviets to Apollo 11 in 69. And I think to a lot of people, there was just an expectation that it would continue if they weren't in touch with how unpopular some of that spending had become. So you got to look back at the space race sometimes with a critical lens sometimes, that sometimes the story is told a little too simply, because at the time it was not so straightforward. And if you were to ask Soviet apologists of the 70s and 80s, we never said going to the moon was the ultimate objective. So that in hindsight, it's nice to say this place I got to is the ultimate objective. It's like, well, were you even in a race, or did the other person not even know you were racing?
Yeah, it's a convenient American explanation, but I mean, even just looking at the slides that you presented right now, Phil, the Soviets beat the Americans to the surface of Venus. We've never landed on the surface of Venus before. So they were still doing things in space after humans stopped going to the moon, in terms of Venus and Mars. I mean, their efforts at Mars were not very successful, but they were trying. So, it's not the entire space race ended just when humans stopped going into space.
And I would like to say a word too about what I consider to be one of the just most wonderful developments that has come out of space exploration, and that has been the robotic exploration of the whole solar system. Just uncovering the wonderful discoveries that have been made all the way out to Pluto and beyond. The asteroids, the outer planets, their moons, just incredible. And I just think that's wonderful. And that came along, of course, after Apollo. So the space race didn't end exactly. It's just that it changed its complexion completely. But what's been happening since has really been fantastic.
Yeah, absolutely. And this is what robotic exploration of the solar system, orders of magnitude cheaper, obviously much safer, and we get to learn about many, many worlds instead of just the one. Okay, let's move on. After consuming the content on the Apollo missions, I was wondering what kind of qualifications and skills were looked for when selecting astronauts during the space race. For example, were they typically veteran pilots or engineers? I was also wondering what the key skills and experiences are looked for in today's astronauts. Um, so, in terms of the earliest astronauts, certainly the Mercury 7 and the Gemini missions, almost exclusively test pilots or experimental flight pilots. Um, Most of them having military service or at least some sort of relationship or enrollment in military organizations.
Yeah.
But not all haven't been combat pilots or anything like that.
No.
But that would certainly shift after kind of Apollo. But Apollo does see a few non-pilots. And after Apollo, once we get into the shuttle and stuff, that's way different. But Phil, in terms of just the Apollo era astronauts, we're seeing almost exclusively pilots.
Yeah, that's right. And I suppose in a way it had to be that way because the same test pilots who were doing things like breaking the sound barrier, Chuck Yeager and so on, those people, they would be the natural people to choose to stick them on top of a missile and fire them up into space, because who else is going to be better at handling that? It would be natural. So it's completely different now, but that was natural at the time. And I suppose the space shuttle was the thing that kind of produced this split, because on a space shuttle flight with, say, 6 or 7 people, you could have a couple of people who were functioning primarily as pilots and who understood every detail of the orbiter so that they could fly it. And then you could have mission specialists who were involved in scientific experiments or in operating other kinds of equipment. So we started to see that split with people who were primarily something else, an engineer, a doctor, that kind of thing, a physicist, say, coming up as astronauts as well.
And before I go to Tanya, because I know you interact with current people who go to space or astronauts. Yeah, I mean, once you got to the place where you have up to 8, but typically 6 or 7 people on a shuttle mission, certainly they don't all have to be pilots. But in the Gemini program where you had up to 2 people, and Apollo where you had 3 max, you probably want all of them to be able to operate the thing if emergency calls for it. But also just space flight at that time was still essentially an experiment. The shuttle, especially by the time in the aftermath of the Challenger disaster, became not routine, but not entirely an experiment. So you didn't need people who were geared for, I'm in a thing that might blow up. You needed people, the original Gemini and Mercury astronauts really had to take on the mindset of like, we don't even know if this thing works. Whereas thankfully, by the time the shuttle came along, there was some sense of like, well, we know it works, so we just need specialists. But Tanya, you know people like Cyan Proctor and stuff who've been to space and are astronauts. Today, it's a whole different world, obviously.
Yeah, I mean, I think today really the main requirement is, can you physically handle what happens to your body as you go into space? And then the rest, I think, kind of depends on how much time you're going to spend up there. Like if you are, a space agency astronaut that is going to spend months on the space station, are you good at completing very specific tasks at a very specific time schedule? And will you not go crazy being in a confined environment? And will you not drive the other people around you crazy? So I would say the personality that you see in a lot of, shuttle era type astronauts is kind of the polar opposite of what you see in these test pilot maverick kind of guys that have like a lot of bravado and a lot of swagger. I guess saying swagger sounds like an insult to the shuttle astronauts, but I mean in just like the way they carry themselves. The shuttle astronauts tend to be a little bit more reserved, like
Team oriented, right? Like,
yeah, team oriented people. They're not out there trying to steal the show for the most part. And so I remember a woman when I worked at ASU who did research on personalities of astronauts over time. And she made the comment that like you would never put Neil Armstrong and Buzz Aldrin together on a Mars mission because they would kill each other. Like it's not a good personality fit.
Yeah.
But maybe someone like Neil would be really good with other Neil-like people on an extended space station mission, for example. But now I think we're shifting even more because you have commercial astronauts, like companies like Axiom are launching people to be astronauts, like completely separate from space tourism, but actually like people that are doing jobs as being a commercial astronaut. And there, I think it's the same kind of like, are you physically up to getting into space and handling the environment up there? But there's not even the sort of political requirement of, is this somebody that would look good to be a National Space Agency astronaut? The companies are just like, can you do the job? And that's probably really all they care about.
I mean, I'm sure there's still some PR considerations in terms of this is going to be a face of the company and stuff like that.
That's true. No serial killers or anything like that.
Yeah, but it is interesting to think about, the complete shift. And obviously now one of the dominant considerations for any long duration space flight, which we may still be quite a ways away from, but I mean, if you're going to be stuck in a can with someone for 6 months on your way to Mars, I think one of the most important things is going to be a psychological assessment of those people, because their lives are going to depend on one another, and they're going to be in some pretty significant duress. So as we go forward, I think increasingly psychological and psychiatric considerations will be pretty heavy.
Especially in a Mars mission where at some point when you've reached a critical distance from Earth, you have no more real-time communication with any other human except the people that are on that ship with you. And that is so foreign to how most of our world operates today. Yeah. Even though we try to simulate time delay in communications through things like analog missions, I think psychologically, you still always know you're on Earth. If something goes wrong, they can airlift you out or send an ambulance or something. When all of those safety nets are gone. And I mean, we even have those on the space station, right? You can get in the escape capsule and come home if something catastrophically goes wrong. On Mars, that's not an option. Like if something goes wrong, you're probably going to die. How are those people going to handle that?
All right. Let's move on. Last question. I'm really curious, Phil, if you have any sort of like serious analysis or knowledge of this, because I've never actually heard much about this. But okay, the question is just phrased simply. What caused the US to use chimpanzees versus the dogs that Russia used?
Yeah, well, that is very interesting, isn't it? I don't know how much of a kind of analysis of different species was done to try to decide. I think, yeah, probably. I think Americans probably went with chimpanzees, thinking that they were the closest analog that you could get to a human that could potentially fly. I mean, there are other apes, but they're much bigger, so you get, chimpanzees might be more convenient from that point of view.
Giant silverback
gorilla. They in many other respects they have some degree of commensurability with humans, say in the ability to to manipulate things or something like that. So maybe they're thinking this is the closest analog we can get. I'm more interested really in why the Russians chose to fly dogs. I mean, that goes all the way back to 1957 with Sputnik 2 and the little dog Laika. I don't know why they made that choice, except of course that dogs can be trained. Dogs are, well, I guess they're easy to track down as well and find. But many people have a very special connection with their dog, and maybe there was just some feeling that these animals are kind of emotionally close to us, and they're trainable, so we'll use them. But I don't know to what extent people might have looked at other creatures, or just doing a direct comparison of those two to see which was best. It just kind of happened that way, I think.
Yeah, I think you hit on all my suspicions too, especially about the choice of dogs. I mean, the breed that Leica was this a kind of terrier, essentially, quite small. And the space Luna 2 was not a large spacecraft, so certainly you want a small animal that's intelligent enough to teach basic commands. And I don't think monkeys were readily available in the Soviet Union would also be my suspicion. I don't know that for sure, but I'm assuming there's a lot more terriers running around than macaques and
Yeah, that's right.
long-tailed
Yeah.
monkeys.
Right.
So that might be the reason. Yeah, I think the propaganda reason is reasonable as well, to assume that this is a all Russian. I don't think it was a Russian species, but this is a dog that Russians of the time could relate to. That was a big part of their advertisements for their space program too. It was like anyone can be an or cosmonaut. And then with the chimps, I mean, it was also just kind of trendy at the time in the 50s and 60s to have like smart animals, and chimps and horses, oddly enough, were like constantly on like Ed Sullivan and those kinds of shows doing tricks. So I think chimpanzees, like you said, trainable, much more intelligent than dogs, but quite large animals. And I guess, I mean, certainly Ham and the other ones, their spacecraft would have been way larger than what Leica went up on.
Oh yeah.
But I mean, this is an opportunity for me to rant and rave that sending animals to space makes no sense. There was, I don't think, any scientific value to anything, like nothing that a barometer and a thermometer couldn't have told us anyways. I don't know
Especially
what.
since, like, even if they survived coming back, then they still killed a lot of them anyway to study them, which is horrible.
Yeah, I don't know. Phil, maybe you know more, but I've never really seen any evidence that there was meaningful scientific knowledge gained that couldn't have been gained alternatively.
No, it's not something that I've studied very much. But,
Yeah,
I find
I
it
don't know,
hard
but
to imagine.
yeah, I don't know. The poor animals they don't want to be there. All right. Well, on that note, Tanya, you froze there for a bit. You okay?
Yeah, it seems like it still was recording. I could hear everything you guys were saying, but all the video was frozen.
Okay.
So I think we got that whole answer.
Okay.
All right. Well, that sounds good. This one's been a bit of a long one, but we can probably edit down. Certainly, there's stuff at the beginning that we don't need. And then, yeah. Okay, sounds good. So thank you, everyone, for watching. Thank you to students for watching. And we shall see you all once again for Space Club in another month.
Okay. Bye.
Bye, everyone.